This is the equivalent circuit of a lossy transformer that I had shown you last time. I'll be coming back to it again and again, but I thought I would remind you of this particular one once again. Symbols may change a bit depending on where you look. The lossless transformer, which is the ideal case, is in the middle of the diagram, where the primary EMF EP and the secondary EMF ES are shown. They are obviously connected by the turns ratio NP divided by NS. Okay, so I'll come back to it later. Let me move a little bit further in this document in terms of basic theory of the transformer. It's not very difficult. If you look at an ideal lossless voltage transformer, the schematic that is normally used to describe the operation is what is shown in figure 1. You show two coils coupled with each other. Primary coil on the left side having NP number of turns, secondary coil on the right hand side having NS number of turns. In between, we draw two vertical lines to show the coupling. Since it's a lossless case, the applied voltage on the primary VP would fully appear across the primary coil because there is no loss in the connecting wires. And similarly, the EMF generated on the secondary side will fully appear across the load connected to the two terminals of the secondary winding. We are assuming load to be a real quantity, that means a resistor, but it doesn't have to be that. Okay, so this is the simplest description you can think of when it comes to a transformer. Vp divided by Vs equal to Np divided by Ns, and Vpip equal to Vsis, assuming power factor is 1 and all that, and losses are 0. Last time I had shown you a PPT where we discussed a bit about the losses also. Losses are primarily coming from two different things. One of them is the fact that wires used in coils have finite electrical conductivity that generates the so-called conductor losses. And the second factor is the coarse magnetic materials imperfect behavior. There are losses like hysteresis loss, eddy current loss that make what we call core loss or magnetic loss. Okay. And all that has been captured reasonably accurately in this equivalent circuit, which is a much better and much more accurate description than what is shown in figure 1. But figure 1 helps you in understanding the concepts quickly without having to worry about losses. Okay. The terms used are shown here in writing. NP is number of turns in the primary winding. NS is that in the secondary winding. VP is the applied voltage to the primary winding. VS is the resulting voltage in the secondary winding. If VS is lower than VP, it's a step-down transformer. If VS is higher, then it's a step-up transformer. RL is the load resistance. IP and IS are the two currents. Now, the voltage generated in primary and secondary, we call them EMFs because they may be different from the applied or available voltage in case of a lossy transformer. So the EMFs generated in primary winding and secondary winding can be uh, can be described by means of some equations, which I'm going to show you now. These equations are derived based on Faraday's law. Assuming that the flux, magnetic flux generated in the core is phi, and it's a function of time, obviously, because the input voltage is a function of time, and its periodic function, that is also a definition. Unless otherwise stated, we will assume periodic function. So Faraday's law says that the instantaneous value of the EMF generated in the primary winding will be minus number of turns into d phi by dt. Number of turns is NP in the primary winding. And we are ignoring leakage of flux, etc., etc. Similarly, in the secondary winding, the instantaneous value of the EMF will be minus ns into d phi by dt. Phi is common between the two windings because core is the same for both. Okay, so that's the starting point for both the windings. Now, suppose phi is known to us and can be written as a sinusoidal function. We are talking time domain right now. In the time domain, it is written as phi m sine omega t, where phi m is the peak value of the flux. Flux is measured in Weber. Omega is, of course, 2 pi f. You know that quite well. It's the angular frequency. Which is related to the operating frequency by 2 pi f formula. Okay. Now, if I take equation 3 and substitute it in equation 1, I get a very interesting formula for Vp. This is what I get. d phi by dt will be omega phi m cos omega t. That I'm going to put in equation 1, in fact, even in equation 2, to write the equations for Vp and Vs in terms of time. So this is what I get for Vp, and similarly for Vs I get equation 6. So the peak value of Vp is Np phi m omega. Forget minus sign because peak value, we are talking magnitude. And for the Vs, it is Ns phi m omega. RMS value will obviously be peak value divided by square root of 2. So the RMS value of primary EMF, let's call it Vp, will be omega Np phi m divided by square root of 2. And omega is 2 pi f. So I get 2 pi divided by square root of 2 multiplied by f Np phi m. And similarly for Vs, RMS value, I get this formula. Equations 9 and 10 are known as EMF equations. In fact, 2 pi divided by square root of 2 is approximately, I think, 4 point something. We will come to that in a minute. So some books write that rather than writing 2 pi divided by square root. Now, another parameter that is brought in is flux density, magnetic flux density, Bm. If the area of the cross section of the core is capital A, then the flux divided by area is known as flux density. Question 11 essentially defines Bm. Commonly, this is given to you rather than phi m. Commonly, it is a Bm value that is given to you. The unit for Bm is Weber per meter square. It is also known as Tesla, Tesla. Okay. 1 Tesla is 1 Weber per meter square. So if I use that notation, then in both equations 9 and 10, I can remove phi m and put BMA, where A is the area of cross section of the core, which is known. And 2 divided by square root of 2 is square root of 2. So keeping that in mind, I get these equations. EMF induced in primary and EMF induced in secondary are given by equations 12 and 13. These are RMS values. Now it is obvious that Vp divided by Vs is Np divided by Ns. This is what I had told you right in the beginning. Now we have proven it. And Np upon Ns is known as the turns ratio. We denote it normally by small a. Because it's a lossless transformer, and we will assume power factor equal to 1 throughout. VPIP should be equal to VSIS. Input power should be equal to output power. Transformer is not an active device. It will not generate power. It will take whatever is coming in and pass it on the other side. So the other equation that comes out is Vp divided by Vs equal to Is divided by Ip. And that is, of course, small a. Okay. Now, one interesting property the transformer has is that if you connect a load RL on the secondary side, it gets transformed to some other value when seen from the primary side. That is called impedance transformation. If you connect RL on the secondary side, it will look like something else. If you view its effect from the primary side. Let me look at what happens, what theory it says about that. Suppose the load connected is RL, let's say it's a resistive load, then Vs equal to RL into Is, simple Ohm's law, right? Vs is RL into Is. And we define input resistance as Vp divided by Ip. Vp divided by Ip. That is the hypothetical resistance, which we call input resistance. By the way, this can be generalized for complex loads also. You simply remove capital R and put capital Z. That's it. Theory doesn't change because of that. Only thing is you'll have to deal with complex numbers when making calculations. So if R in is Vp upon Ip by definition, and Vs is also, rather, RL is Vs upon Is. Let's see what happens to Rn. Vp is AVS, right? And Ip is Is upon A. So I put that there. What I get is A square Vs divided by Is. And Vs divided by Is is RL. So input resistance is A square times the load resistance. This is ideal lossless case. If I had a complex load ZL, then input impedance Zin would have been A square into ZL. That's it. So the impedance gets transformed, the load impedance gets transformed by a factor which is the square of the turns ratio when you go from secondary to primary. This property is very useful for high frequency transformers. For power transformers, it is better to keep it in mind while evaluating the performance. Yeah, for complex load, equation would be generalized to Zn equal to A square Z. Interesting property of a transformer. Now, some interesting simple problems. Very easy. It takes more time to read them than to solve them. An ideal voltage transformer has primary voltage of 480 volt and secondary voltage of 120 volt. These are RMS values by default. If the primary winding has 700 turns, how many turns are there in the secondary winding? Simple. Turns ratio is Vp upon Vs. So 480 divided by 120, which is 4. So Np upon Ns should be 4, and Np is given as 700. So Ns should be 700 divided by 4, which is 170. Simple. Okay. Then next one. For the transformer considered in problem 1, this one, if a purely resistive load of 240 ohm is connected across the two terminals of the secondary winding, calculate the resulting currents in primary and secondary winding. Secondary voltage is 120 volt and you are connecting a load of 240 ohm. So secondary current will be 120 divided by 240 amperes, 0.5 amperes. And primary current we know is equal to Is divided by A, and A is already known as 4. So 0.5 divided by 4 ampere, which is 0.125 ampere. Done. Okay, continue. Problem 3. For the transformer considered in problem 2, what is the power factor of the load? Well, obviously it's 1. You are using a pure resistor. What is the input power? Okay, that's a good question. The output power and the efficiency of the transformer. Power factor is 1. There's no question about that. Now, it's a lossless case, so efficiency will be 100%. I can see it intuitively. P out and P in will be the same, but how much are they? PI will be P input will be IP, and VP is 480 volts, IP is 0.125 ampere. So 480 volts into 0.125 ampere. You should do the calculation, you should get 60 watt. Okay. And similarly, if you do on the secondary side, VSIS, then VS is supposed to be 120 volt and IS is supposed to be 0.5 ampere. So 120 into 0.5, that also should give you the same answer, 60 watt. So input power equal to output power equal to 60 watt. And efficiency is output power upon input power, 100%. Lossless case, obviously. Now, let's try to complicate our life a little bit. Okay, it's not done here right now. We'll do it later. Before we do that, let me reiterate what I was trying to tell you last time, that the diameter of the primary and secondary wires will be determined by how much maximum current each windings are supposed to be getting. Once IP and IS are known and maximum value, okay, use table 1 to figure out the wire size that you would need. I was telling you last time that in the market, you cannot get any arbitrary diameter of the wires. There are standard values that are available, and they are given either by American wire gauge system, AWG, or standard wire gauge system, which is the British equivalent. I am showing you AWG values, but SWG values are also available, and they are fairly close to all this. In AWG system, if you look for number 1 wire, it will have a diameter of 0.8 inches, quite thick. In millimeter, it will be 7.34822. Area of cross section, you can calculate pi by 4 into diameter square. You will get 42.4 millimeters square. Resistance per 1000 feet length is also known to us. R, you remember in transmission lines, we define RLGC. This is the capital R value for that wire which is being used. And per kilometer also the value is given, fine. Maximum current number 1 wire can carry is 150 amperes. This is probably the thickest available. I'm ignoring super thick wires. There are very special wires also available, which are very expensive, by the way, like 0.000 size or 4 divided by 0 size. That's a very thick wire, 0.46 inches, and it can carry up to 300 amperes, 302 amperes current. Then 0.000 wire is also there. You try to avoid them; they are very expensive, I know. But this guy also can carry very large current, 239 amperes. Then 0.0 wire is also there, which can carry 190 ampere. And then we have zero. I think I am making a mistake in reading. Sorry about that. Yeah. Actually, it's 0 number wire, which can carry up to 150 amperes, and 1 number wire, AWG1, which can carry 119 amperes. And frequency, maximum frequency of operation is also known for all these wires. You can see that the thinner wires can go up to higher frequencies. So this table, if it's available to you, will help you decide in choosing the AWG size of the wires that you want to use in the primary and secondary. In fact, if you cannot get exactly the size you want, you go for the next thicker wire to be safer. Okay, here is the problem. For the transformer considered in problem 3, that means this one, and problem 2 also, yeah, same thing. What AWG size wires would you choose for primary and secondary winding? So you need to remember the current, and current values are all RMS values in the table also. So primary winding, let's say full load current is known to us 0.125 amperes. So try to read 0.125 ampere in the table or close enough. The closest is 0.142. You want to be safer, so go for the next. Don't choose 0.113. It is lower than what you need. So go for the next higher value. The current of 0.142 ampere is supported by number 30 wire. So for primary current, I would recommend AWG 30. Yeah, AWG 30. Okay. For secondary current, the value is 0.5 ampere. So let's go back to the table. Choose 0.5 or closest. So I guess 0.577 will do the job. Don't choose 0.457. That's lower than what you need. 0.577 is safer. I hope I'm reading the current. Yeah, it is maximum current. 0.577. This will be 24 number wire. So secondary will have 24 number. Okay. Table has to be with you, of course. Nobody can memorize the table. That's for sure. Now, a single phase transformer has NP equal to 1000, NS equal to 200. The maximum value of the flux density in the core is 1.1 Tesla, which means 1.1 Weber per meter square. When 2200 volt, 50 hertz is applied to the primary winding. Calculate the cross-sectional area of the core. What you will need is the EMF equation. This one, either VP or VS, depending on what is being given to you. I have not written here, but many books actually write instead of square root of 2 multiplied by pi, they write 4.443 or 4.44, which is approximately correct. So you may see 4.443 instead of square root of 2 pi in the books. Let's see. Yeah, actually I have written it here. VP is supposed to be this, right? We have proven it. And that works out to 4.4429 if you want to be super accurate. Now in this equation, you plug in all the values. VP is 2200 volt. Okay, which is given to you. Frequency is also given as 50 hertz. Number of turns in the primary. Where given? Yeah, 1000. Good. And the flux density peak value is also given as 1.1 Weber per meter square. BM is given. So everything is given except A. You do the calculations. I have written the formula to bring A on the left hand side, and then I have done the calculation. You can double check this calculation. The answer turns out to be that the area of cross section is approximately 9 multiplied by 10 raised to the power minus 3 meters square. You may convert it into centimeter square. 1 meter is equal to 100 centimeter. So 1 meter square will be 100 into 100 centimeter square, which means 10 to the power 4 centimeter square. So the answer could also be written as 90 centimeters square. I could have used the equation for Vs also, but then using the turns ratio, I would first calculate Vs, and then I would use. I should get the same answer. that way also. Since the turns ratio is 5 and Vp is 2200, Vs will be 2200 divided by 5 volts, which I think will give you 440 volts. So you can have 440 equal to 2 pi divided by square root of 2 f ns BMA. Use that. You should get the same value of A that we are getting here. Next one. A source which can be represented by a voltage source of 8 volt RMS. Very interesting problem. Read it carefully. A source which can be represented by a voltage source. It should be ideal voltage source actually. A source which can be represented by an ideal voltage source of 8 volt RMS in series with an internal resistance of 2000 ohm. See, real life sources have internal impedance or internal resistance. Ideal source ignores that. We at least we try to ignore the effect. So let's assume that we have a real life source which has got 8 volt RMS value and it has an internal resistance of 2000 ohm. And this source is connected to a 50 ohm load resistance through an ideal lossless transformer. Now, what should be the turns ratio of the transformer for which the power supplied to the load is maximum? Good question. And then you find the corresponding power also. It's a bit of derivation here that we would need. A source which can be represented by a voltage source of 8 volt RMS in series with an internal resistance of 2000 ohm is connected to a 50 ohm load through an ideal transformer, voltage transformer obviously. Calculate the value of the turns ratio for which the maximum power is supplied to them. So we want to maximize the power dissipated in the load. What should be the value of small a for that? Let's see how I did it. For maximum power in the load resistance as seen between the two input terminals of the primary winding must be equal to the source resistance, which is 2000. This is maximum power transfer theorem. Let me go back to the diagram of the ideal voltage uh, transformer. Here, the value of RL when transformed to the primary side will become A square RL. And then you are connecting you're connecting a source to the primary winding, which has internal resistance, which is known to you. Maximum power transfer theorem says that for maximum power transfer, the load and the source impedances have to be complex conjugate of each other. The load RL will become A square RL when seen on the primary side. So A square RL and the resistance of this source that is connected, they should be complex conjugate of each other. Fortunately, they are both real anyway, so they should be equal. Complex conjugation is not necessary because these are real numbers. That is the condition for maximum power dissipation in the load. Yeah. So the input resistance because of the load will be A square RL, and that should equal the source resistance, 2000 ohm, for maximum power to be transferred. So I equate 2000 to A square RL, and RL is known to me as 50 ohm. From there, I figure out the small a value required. It is square root of 40, 6.325. It is not an integer value, unfortunately, but I cannot help it. We are not determining the actual number of turns. We are determining only the ratio of the two number of turns. Okay. Actual turns, etc., will depend on how much is the primary voltage magnitude, how much will be the secondary voltage correspondingly, and so on. But that is not necessary to do in this case anyway. They are not asking you to do that. Now, the second part of the problem is calculate that load power which is transferred when this condition obtains. Primary current, obviously, I've drawn the diagram. Yeah, this is better. Now you can see what this is how it is. You have the source, the internal resistance of the source, the load on the right hand side, which is transformed into A square RL on the left hand side. Okay. So A square RL and RS are equal for maximum power transfer. So the total current, total primary current will be Vp, which is 8 volt, divided by RS plus A square RL. And RS and A square RL are equal anyway. So Vp upon, I guess I am calling it Rin rather than RS. Fine. But Vp upon 2000 plus 2000, which is 8 upon 4000 ampere, which is 2 milliampere. That will be the primary current under this condition. Secondary current is A times Ip. We know that A is square root of 40. So approximately it works out to 12.65 milliampere. Now maximum power supplied will be obviously Is square RL. So do the calculation. Is is 12.65 milliampere. Square it, multiplied by 50. You should get about 8 milliwatt. That's the answer. In fact, you can write a MATLAB program to calculate the power dissipated in the load versus the what should I say, versus the value of the load. You will see an interesting curve which will show maximum when RL equal to 50 ohm under these conditions, assuming that A is square root of 40 and so on. Other thing you can do is maybe plot the value of Is square RL versus small a. Lot of investigations can be done using the basic theory. And there also, you will see that the peak of the total power dissipated in load will occur when small a happens to be approximately equal to square root of 40. I'm not asking you to do it because obviously MATLAB, etc., cannot be part of the exam for sure. But it's an interesting project to put it all in MATLAB and do some studies. Okay, next one. A doorbell requires 400 milliampere at 6 volt. It's AC, of course. It is connected to, the supply that comes to our home is not 6 volt. So doorbell cannot be directly connected to it. You need a transformer, step down transformer from 220 to 6 or 110 to 6. In the US, the supply is 110 volts. So you'll have to step down from 110 to 6 volt. In this country, you'll have to step down from 220 to 6 volt to make the operation safe. Otherwise, doorbell will simply burn out, if you apply that supply voltage directly to it. So anyway, that is what the question is all about. A doorbell requires 6 volt and it also requires 400 milliamperes, correct, to operate. It is connected to a transformer whose primary contains 2000 turns and it's connected to a 110 volt household outlet. This is US, this is American problem. Okay. In our case, it is 220 volt household outlet that we have got. So how many turns should there be in the secondary? This is a simple question. 110 to 6 stepping down, and primary turns are 2000. To calculate secondary turns will be very easy, I think. This is how the connections are also. This is the outlet voltage, 110 volt. It is connected to the primary of the step-down transformer. You choose NP and NS carefully so that VS happens to be 6. And IS also is given to you actually. IS should be 400 milliamperes, I think. Yeah, it's all given. So let's see. VP is 110 volt, VS is 6 volt, NP is 2000 given to you. So VP divided by VS, which is 110 divided by 6, which is 55 divided by 3, should be equal to NP divided by NS. NP is 2000 given to you. From here, it's easy to figure out NS. NS turns out to be almost 109. So the transformer secondary winding should have almost 109 turns. Then it will give you 6 volt. Okay. If the number of turns in the primary were different from 2000, obviously NS would also change accordingly. Now we will assume ideal lossless transformer. So VP IP equal to VS IS. From here it's easy to figure out IP. IS is known as 0.4 ampere, 400 milliampere. Yeah. Okay. VS is also known as 6 volts. VP is known as 110 volts. Easy to figure out IP. It is almost 0.0218 ampere, which is 21.8 milliamperes. The input power will be VPIP. You can do the calculation, it will be 2.4 watt almost. You can do the calculation on the output side also, VSIS. It should also be equal to 2.4 because we are assuming lossless transfer. Next one. Okay, there's no numerical problem. In fact, I want to talk about dot convention. I had told you last time also that manufacturers show dots in the schematic of the transformer. If both the dots are on the top, what says when one dot is on the top on the left side and the other one is at the bottom, the phase relationships between VP, VS, IP, and IS are different. Basically, the direction in which windings are done are not known to you. So vendors try to tell you all that by using a dot convention. And that's what I'm talking about here in my notes. Yeah, the dot convention. We generally assume that the primary and secondary voltages and currents are in phase. I guess not a bad assumption. Generally, that is the case, yes. In reality, this depends on how each winding is wrapped around the core. Manufacturers use dot convention to describe the phase relationships on the symbol of the transformer. Dots on top for both primary and secondary windings. In this case, VP and VS and IP and IS are in phase. Also, IP and IS are in the same direction. IP is flowing in, IS is coming out. This is the way it should be. Okay. And in case 2, if the second dot is on the lower side, VP and VS and IP and IS are 180-degree out of phase. And also the directions of IP and IS are opposite to each other. Both are going in. That's the way it is. Good to know that These are, by the way, universal notations. All transformer manufacturers have to obey them. By default, if nothing is given, you assume case 1. That means VP, VS are in phase, IP, IS are in phase, IP is going in, IS is coming. That's the assumption by default. Losses. I had told you last time about losses. Let's go over it once again. A transformer in real world is never lossless. Instead, there always exists a difference between input power Pi and output power Po. This difference, measured in watts and denoted by, say, PL, that means P loss, is given by PL equal to Pi minus Po. Input power in watts minus output power in watts is the loss power in watts. Simple. Okay, common sense. It applies to all machines, in fact. Now, efficiency is obviously PO divided by PI, power efficiency for sure. You can multiply it by 100 to get the number in percentage. Not a big issue, right? Yeah, it's all written here. Now you can write PO as PI minus PL. So another way of writing efficiency is 1 minus PL upon PI. If PL is 0, we have a lossless case. Efficiency is 1. Okay. So that's the symbolic description of losses and efficiency. Now, nature of losses. The two main types of losses in a transformer are copper loss and iron loss. Iron loss is also known as core loss or magnetic loss. That is because of the material that you are using for building the core. Copper losses are because the copper wire used, or even aluminum wire if used, for building the windings has finite conductivity. Stray losses is another word you will like to keep in mind. This means things that you normally don't expect, but they are still happening. Funny things can happen. It may not be so serious for transformers, but for rotating machines, which we are going to talk about after the midterm exam, their stray losses are a lot more seen compared to the case of transformers. But stray losses means things that are not expected normally. If there's a lot of wind flowing, it may affect the operation. That's one example. That is called windage loss actually. If it's a rotating part, which we are not doing in transformers, of course, but if it's a rotating part, then friction is also there, which is called a mechanical loss. But all that I'm avoiding right now. In transformer, it's better not to talk about all that. The two most important losses are copper loss and iron loss. Copper loss obviously is IP square RP into IS square RS. Sorry, plus IS square into RS. IP is the magnitude of the primary current. IS is the magnitude of the secondary current. RP is the resistance of the primary winding. RS is the resistance of the secondary winding. Now, RP and RS can be easily calculated. Suppose I had chosen wire number 30 for one of the windings. I would know how many turns I'm using, and based on that, the diameter of the coil is also known to you. Based on that, you will know how long the total wire length, how long the total wire would be. So you will take the resistance per unit length and multiply by the length of the wire to get the total RP value. Similarly, for the secondary also, you can get the total RS value from this table, and after knowing the total length of the wire in that coil. But anyway, these values are given to you in exam, in most of the textbooks. These RP, RS values are given to you. You don't have to worry about calculating them. So once you know RP and RS and you calculate IP and IS as we have done in several problems today, the copper loss, which I am denoting by PC, can be calculated using equation 25. It will be in watts, obviously. As the transformer is loaded more and more currents are drawn and copper loss starts increasing with the square law effect because you have square of the current. So you got, and in the windings start getting hot. If the design is not done correctly, windings may start melting. Fires would begin. Accidents would happen. Deaths might occur. Almost every day in the newspaper, you read about transformer accidents. Oil is there to cool the whole thing. And if fire starts, oil catches fire. It can be very dangerous. Okay. So copper losses are very serious. You got to be very careful about designing the transformer and figuring out the worst case copper loss and making sure that heat has been suitably eliminated. Mechanical engineers play an extremely vital role in transformer design. Iron loss, the second part. Even core gets hot, but again, it is generally not going to catch fire. It is made of a solid material. While windings are made of thin wires, they are not very thick. So chances of melting are much higher. But yeah, core losses cannot be ignored also. They are serious too. Core or iron loss or magnetic loss, whatever you want to call it. Here I'm saying iron loss. Okay. Iron loss is caused by core material and the method of core construction. Yes. This loss is composed of A, hysteresis loss, and B, eddy current. Hysteresis loss is due to the reversal of magnetization in the transformer's core. First, the top half and the bottom half of the cycle behave differently as far as the material is concerned. The bottom line is that we have got approximate equations to calculate the hysteresis loss in watts. You don't have to worry too much about derivations here. This equation is semi-empirical anyway. If you know the flux density in the core, raise it to the power 1.6 multiplied by frequency, and V is not voltage, it is the volume of the core in meter cube. And K is an empirical constant whose value is known for a given material. Typically, it is from 1.5 to 2.5. Okay. This formula actually has been derived by this gentleman. I cannot pronounce his name. He's a German guy. But because of that, K is known as a constant in his name. Okay. Eddy current loss is because of the local current setup. And I told you last time that instead of making the core solid, we make it out of thin wafers, which are bolted together or glued together. Some part of the flux generated in the core links to other parts of the core, thereby setting local currents called eddy currents. This dissipates some energy of the core, some energy in the core itself. This is known as eddy current loss. There's an approximate formula for this also. Here, second order effect is there for BM, while for hysteresis loss, you had a power of 1.6. So eddy current loss actually rises higher, rises much faster with the flux density. Frequency square is involved here. There it was frequency to the power 1. T is the thickness of the wafer, each slice, how thick it is. That is small t. Okay. Anyway, the reality is that these losses are measured experimentally for most of the practical cases. These equations are good to know, but I'll tell you much later maybe how experiments are done to calculate iron losses for a given transfer. But in case that data is not there, you can use these equations to approximately know the magnitudes of these losses. Now, this is the equivalent circuit of a lossy transfer. You start with the input voltage applied to the two terminals coming out from the primary side, Vp, and some current Ip will go in. These may be complex numbers in general. Okay. Then the winding will have some resistance and some inductance also. So Rp plus Jxp equal to Zp is the primary windings impedance. Generally, Rp is a lot more serious than Xp, but still, there are times when Xp may also be appreciably large. Then the course effect is taken care of by putting a circuit in parallel with the primary. This is all approximate description, by the way. It's not 100% accurate, but close enough. The core magnetizing current, core, by the way, will be continuously magnetized. Even if you connect nothing to the output or the secondary of the transformer, even then core current would continue to be there. Core doesn't stop working. Even if IS is 0, that will only mean that the current on the right hand side of the parallel circuit will not be there, but from the left hand side, some current will have to be supplied to keep the core going. Okay. So I phi is the core magnetization current, which would always be there, no matter whether the load is high or low or not there. The core remains working. Okay. I phi has got two components. One of them is the core loss component, which is approximately described by a resistive component R0 or R3. In many books, they call it R3, and a magnetizing component called XC or XO. These values are given to you again. Again, experiments are conducted to calculate these equivalent circuit parameter values. For your convenience, these values will be supplied to you for a given transfer. After these losses have been accounted for, then the remaining voltage would actually be the EMF in the primary, EP, for which we have got the equations. And then that will be stepped down or stepped up based on the NP upon NS ratio to the secondary EMF. And from that secondary EMF, again, there will be losses in the secondary side, which are accounted for using an equivalent parameter called secondary impedance, ZS, which has secondary resistance and secondary inductance in series. So that is roughly our technique to try to analyze the performance of a transformer in real life. This equivalent circuit gives us reasonably good results that will match experimental data. These are the various parameters defined carefully. Rp is the resistance of primary winding, Lp is the inductance of primary winding, Np is the number of turns in the primary winding. Rs is resistance of the secondary winding, Ls is inductance of the secondary winding, Ns is number of turns in the secondary winding, and ZL is the load impedance. By the way, if you are not given some of these parameters, assume they are not there. That's the way this course works. Whatever is not given is not there. If they don't talk about inductance in primary and secondary, assume they are 0, period. If they don't talk about core equivalent circuit parameters, just ignore core completely in the calculation. Sorry. Yeah, this we have done. This we have done. This we have done. This. Don't know where the diagram went, but 1 minute. Should, yeah, here. VP is the voltage applied to primary. EP is the corresponding EMF in the primary. VS is the voltage produced in the secondary out of the second, I mean, across the two output terminals of the secondary. And ES is the corresponding EMF in the secondary. IP is primary current, IS is secondary current. Now keep in mind that IP is the input current, but some of that will be diverted to the core. So IP minus I5 will actually go in the primary. When we do calculations, all this has to be kept in mind. Okay. We have got these formulas for EMFs already. So I'm repeating them here for the sake of reference. For a lossless case, EP and VP were the same. So I was calling them VP and VS there, because ES and VS are also the same. But for a lossy case, it is better to be aware that these formulas apply to EP and ES, not to VP and VS. Yeah, this is something I was telling you, that the magnetizing current for the core has got two components, I mu and IW. IW is known as working current or working component. I mu is actually producing the magnetization. That is, it's producing the flux required. That is called magnetizing part of the total current going in the core. Even if there is no load connected to the secondary, these currents will continue to be there. In fact, the reality is that core loss doesn't change much with the current being drawn from the secondary. It is the copper loss that changes all the time. The circuit containing the parallel combination of core resistance R0 and magnetizing reactance X0 simulates the effects of core losses in the performance of transformer, and the rest of the equivalent circuit simulates the effects of primary and secondary winding on the performance. Okay. If you are given in the problem that core effect can be neglected, you can ignore the parallel path on the primary side completely. But you may still be given the resistance of the primary winding and resistance of the secondary winding, and maybe even the inductances for both the windings. So rest of the circuit would still apply. Okay. Now there's a theoretical condition for maximizing the efficiency of a transformer. It's a very approximate result, but worth going through. Let's look at the derivation. You know that the output power is input power minus loss power. PO is PI minus PL. Simple, right? How does that help? We know that loss power has got two components, iron loss and copper loss. So PC plus P iron, let's say. PC means copper loss. P iron means iron loss or core loss, whatever. Don't confuse. PC is actually copper loss, not core loss. P iron is the core loss. So copper loss is simply IP square RP plus IS square RS, right? And iron loss has got two components, one component due to hysteresis, other due to eddy currents. I'm making them pH and PE. Okay. Now, P iron remains more or less constant with IP. I told you that. It doesn't change. The core more or less needs the same flux, and it keeps drawing that much amount of current that it needs. You can keep playing with the load as much as you want. Core will not care too much. Okay. So if iron loss is not changing with IP, and let's also assume that, which is actually true in a lot of cases, that the secondary copper loss is not that high. Secondary current, in fact, secondary resistance, RS, is generally quite low. We are assuming stepping down conditions, of course. So the copper loss approximately can be written as IP square R, supposing I square RS is negligible. Okay. Under these assumptions, and also keeping in mind that the input power is simply VPIP. I'm ignoring the effect of power factor, although I could have included it, but let me not do it right now. So input power is VPIP. Copper loss power is IP square RP, and iron loss power is simply P iron. Now let's look at efficiency. Eta is PO divided by PI. PO is PI minus PL divided by PI, which is 1 minus PL upon PI. PL is IP square RP, which is the copper loss, plus P iron. I am ignoring copper loss in the secondary. And PI is VPIP. So efficiency is written this way. Now, to maximize this efficiency with primary current, let me do the differentiation of the function with IP and equate it to 0. This is what books do all the time. This is the way I've done it. I'm sure you can do it yourself. So d eta by dip equal to 0 leads to, after simplification, Rp minus P iron upon IP square equal to 0, which means P iron equal to IP square R. And IP square Rp is nothing but copper loss. So what theory tells you is that efficiency will be maximum when copper loss and iron loss are equal to each other. It may not be true. It is very difficult to realize this condition in real life. But at least theory tells you that if you can make copper loss and iron loss equal, you will get almost the maximum power efficiency possible, the transfer. This is called the condition for maximum efficiency. A lot of assumptions are made here, by the way. We have ignored the copper loss in the secondary completely. If we had included that, the derivation would have been a lot more complicated. And if you include the effect of power factor, then also you will get the same result, although I have not shown in my notes, but it's given in the books. Now, I was telling you last time, and I'm telling you today again, that besides the power efficiency, another efficiency which is quite important for transformers is energy efficiency, all day efficiency. Total energy output over a 24-hour period divided by total energy input over the same period, and the entire thing multiplied by 100. This gives you a more realistic description of reality. Of course, if losses are high, all day efficiency will be poor as well as the power efficiency will be poor. If losses are low, both of them will be higher, but they will not be equal to each other. All day efficiency will never be equal to power efficiency. Another important practical performance parameter for voltage transformers is the so-called voltage regulation. We'll be doing a lot of calculations on this later, but today you look at the concept. Magnitude of the no load voltage, that means you connect nothing to the output of the secondary. Okay, that means you'll simply see ES. across the output because IS is 0. So there will be no losses in ZS. So that value, magnitude, of course, is called the no load voltage, no load output voltage, no load secondary voltage, let's say. Then suppose you have connected the load, which is drawing the maximum or rated current. Then how much is the value of voltage across the load, which will be different from no load voltage, obviously. Generally, it will be lower. Magnitude of that. The difference of the two divided by full load voltage and the result multiplied by 100 is defined as the voltage regulation, percentage voltage regulation. Ideally, it should be 0 because you don't want any change in voltage with the load, but practically 5 to 10% value is accepted. And regulation, voltage regulation is defined on the secondary side. Primary side is different. The load is connected. The customer is always connected to the secondary side. Primary side takes the input voltage. Secondary side supplies the customer. So we talk about the customer side regulation, not the primary side regulation. The nameplate of the transformer obviously mentions the recommended primary and secondary voltages and also the frequency of operation for sure. It also mentions the apparent power, kVA, not power factor. We'll work on some problems based on nameplate next time.